Multiple people can live in the same state, the same county, the same city, same zip code, and even on the same street. But multiple households generally don't live at the same street number. Now, I'm not including like apartments or duplexes or things like that. Just like in general, if you were to give like the location of a building, it would be these things. And you couldn't have two buildings in the exact same spot on the earth because one would squish the other one, right? They couldn't take up the exact same space. So we've got the same thing with electrons. Only with electrons we have quantum numbers. And so we have N, L, ML, and MS. And just like with the country, multiple electrons can be in the same N level, the same L level, the same ML level. But when it finally comes down to the MS level, that's where it's going to really separate them out for sure. Because two electrons can't be in the exact same spot, and that's the Pauli exclusion principle. So we're going to learn how to determine N, L, ML, MS. We're going to talk about the shapes of a couple of orbitals, and we'll talk about the radial distribution function and the probability distribution function. All right, so we're going to start with N. And we've talked about N a lot, and this is the same N. It's called the principal quantum number. And with the principal quantum number, there are certain places it can be and certain places that it can't. Or certain numbers that it can be and certain numbers that it cannot be. So with N, it can be any integer starting with 1. So 1, 2, 3, 4, and so on. And the N level tells you how far away from the nucleus the electron can be found. So once we get past the N level, we have the L, which is called the angular momentum quantum number. And it can have values of anywhere. L can actually be 0. And it can go all the way up to 1 less than whatever N is. For instance, if we had N equals 4, L has several options that it could be. It could be 0, 1, 2, or 3, but it can't be 4, and it can't be negative. So it goes from 0 all the way up to 1 less than whatever N is. Does that make sense so far? Okay, good. All right. And with the angular momentum quantum number and the magnetic quantum number and all those kinds of things, it's referring to the fact that, well, it's referring to different characteristics of the way the electron rotates around the nucleus and its direction in space. So they act as if they spin, but they don't know for sure that they spin, but they act like they spin. So you have different characteristics of that. If you get into a class on structure and bonding or physical chemistry, those two things will go over more of exactly what is L and what does it mean. But for now, we just need to know that it has something to do with the orbital. All right, and then we have the magnetic quantum number, which is ML. And if you've had physics yet, you'll find that, oh wait, can I explain what the numbers mean? Yes, and I will get to that. After I explain how you can calculate the numbers, then I'll give you more of what kind of information you can get from them. But that's a really good question. All right, so the magnetic quantum number is ML, and this one can be negative. It can go from whatever L is in the negative value to 0 to whatever positive L is. So for instance, if we go back to n equals 4, L can be any of these values, and let's say that L is 2. Then ML could be anything from -2 to +2. All right, and so when I say that L could be any of these things, it doesn't mean that it is all of those things, that it just could be those things. With an N with a subscript of 0. Let me look. Yeah, and that's really strange. I think that may be a typo. I've not ever seen that value written as M0 before. That is odd. Because even if you look above that, it talks about it being ML. Yeah, I think it's a typo. I'll have to look at it more closely, but I'm pretty sure it's a typo. Yeah, ML can be any real number. ML can be negative or positive as long as it doesn't go below whatever L is or above whatever L is. So I'll give you some examples there in just a second. So when I say that N could be any of these numbers, when I'm talking about a particular electron, one particular electron, and I'm trying to give its address, it only has one N level, one L level, one ML level, and one MS level. And MS is the magnetic spin. And this is where they say that it behaves as if it spins either in the direction pointing up or the direction pointing down. It kind of gives it a magnetic field. And they can pair together because of the magnetic field, even though they're both negative. They don't repel each other because they have a magnetic field. So let's go to some examples. All right, so let's say N equals 4. What are the values that L could be? You just put it in the chat. Could be 3, yep. 1, 2, and 3, perfect. But 0, 1, 2, and 3, yep. Awesome. 0, 1, 2, and 3. And then if we're talking about a particular electron, it would just be one of these. These are just the possible values. In order to figure out what ML is, we have to have a particular value of L. So it could be, let's say it's 2. Not for ML. Let's say L is 2. What could ML be?
0, 2, 1.
So ML goes from -L to +L. Perfect. Those are the values of ml. Now, at this point, it doesn't really matter which value of ml it takes. MS only has two possible values. It could be plus a half or minus a half. And when they write this out, they usually draw a line for an orbital, and then you put your electrons in, and the electrons are these kind of look like fish hooks. Let's see, I think there was a question. Will just be that negative, but perfect. Yes, that's exactly right for the L and the ML. So an electron symbol is just a half arrow. It's like kind of like the fish hook kind of thing. It could be either up or down. So spin up is like this. Ignore this crazy line here. Spin up is like this, and that corresponds to plus a half. And spin down is like this, and that corresponds to minus a half. Yeah, generally, when they get down to MS, they haven't given you enough information, and they probably won't for a couple more chemistry courses. Like maybe when you're a junior, they'll start explaining how to determine what MS is. But for now, they'll say, well, if N is whatever, what are the possible values of L? Or if N is 4 and L is 2, what's the possible value of ML? That's a good question. Right now, you just need to know that one is plus a half and one is minus a half. And it could be either one of those. And when we start doing electron diagrams, which we'll do later, you just need to remember that one's up and one's down, because you wouldn't want to put them in both spin up, because they would repel each other. It'd be like putting two north magnets together and they would just repel. That is a good question. Plus or minus half of what? And that would be half an orbital, because you can get 2 in 1. So this would be half of that space, and this would be half of the rest of that space. All right. So let me give you, you're welcome, an example problem. This is really common type of problem. So I'm going to give you an M, an NL, ML, and MS, and you tell me if there's anything wrong and what's wrong with it. Okay, so tell me some things that are wrong here. Yeah. All right. So I got that the L can't be 2, correct? Because it can only go up, it goes from 0 to N minus 1, and N is 2, so it can't be that. And then plus or minus, well, let's see. Okay, yeah. And then ML is okay, because N couldn't really be 2. What else? There's one more. Yes, okay. Somebody put it right here. Yeah, it couldn't be plus 1. It's either plus a half or minus a half. Perfect. So a lot of times they'll give you a set of numbers like that, and they'll say, tell us what's wrong with these numbers. Sometimes they'll word the question a little bit different. They'll say things like, if N is 4 and L is 3, what are the possible values of ML? Or they'll give you an ML and say, what are the possible values of MS? Or something like that. They'll ask you what the values are. And you kind of get that from I guess just from practicing that, you would pretty much get that. I think what else I want to go over. Oh, I know what. L can be numbers or letters. The reason it can be numbers or letters is because N is integer values, and then L is integer values. And somebody said, hey, wait, that's confusing, which seems silly because they didn't change anything for ML. And those are also integer values. They're just positive and negative. So with L, you make this chart, 0, 1, 2, 3. And then if it's 0, that's an S. If it's 1, it's a P. If it's 2, it's a D. And if it's 3, it's an F. So you can kind of remember it like this. L equals 0, 1, 2, 3, SPDF. And so I never really had a good way to remember SPDF.
Oh.
I just kind of knew it. They're not really abbreviations for anything that I know of. They just gave them letters instead of numbers. But there is a way that you can remember the order of the letters. And this was actually given to me by a student who made it up one day in class. And this is a saying that she came up with. Super poodles do fly. So S, P, D, and F. And of course, you could change that to super poodles don't fly if you like that too. Yeah, it is a little bit. So those are the things. And then a lot of times they'll give you this kind of information and ask you a little bit about it. With N, they call that the energy level a lot of times. It's the principal energy level. Sometimes they just respond as, they just call it the energy level. And so let's say, in this case, looking at N equals 4 and L equals 3, they kind of have a short, it's really an abbreviation, really, but they kind of pair these things together to give you a little bit more information about them. So they would say, well, if L is 3, then it's an F. So then this part is called a 4F. Or they might give you this and say, what is N? And then you would say, well, N is 4. And what is F? F is L. And L equals 3. Some people don't feel that's a good one too. Oh, I got it, Josh. It took me a minute. I thought you were just giving me your opinion of science. And I was like, yeah, kind of sometimes. All right. Let's see what else I want to go over. Okay. All right. So we have orbitals. And in those orbitals, we have subshells. And let's take a look at when L is equal to 1. Let's say N equals 2, L equals 1. If that's the case, ML equals 0, No. -1, 0, and +1. See how it equals three things?
Mm-hmm.
Inside there, I'm trying to think of a really good way to explain it. I'll do it like this. All right. Trying to pick a color. I wish they had more colors. All right, so N equals 2, L equals 1, ML equals -1, 0, +1, and then MS is either +0.5 or -0.5. So one of those values. So let's say I'm drawing out an orbital diagram. The orbital diagram just kind of tells me where the electrons are. And so they give you certain spaces that electrons can be in. And so we have subshells, and we're trying to figure out how many subshells there are. These are the subshells, the little dashes. And that's equal to the number of ML values that there are. So if L is 1, that's a P. So P has 3 subshells. And they call those subshells PX, PY, and PZ. And the X, Y, and Z are the coordinates that you'll find these subshells located in.
Oh.
So when you look at the second section that we read, what was the second one? 3.7, I think? I don't remember. But it tells you about the shapes and the orientations of the subshells. So a P looks kind of like a figure 8, kind of. And I'll tell you more about that in a minute. And it could go in the X direction, it could go in the Y direction, but it could also go in the Z direction as well. So it can go up and down, can go side to side, or it could come out toward you, if that makes any sense. Let's see if there are any questions yet. 3.7, okay, that's good. That's what I thought it was. All right, so let's get into like what shape these things are. So we have L gives the shape. And so we have L equals 0, 1, 2, and 3. It goes beyond 3, but usually we don't get to beyond that. And it goes S, P, D, F, and then goes alphabetically, G, H, I, J, K, L, and so forth. But of course, you get to sort of a little bit of a glitch when you finally get back to S. But electrons don't get that far out. So most of the time, the highest you're going to get is an F. Rarely you might get a G, but I don't think we're going to do that in this class. So that's S, P, D, F. S is easy to remember. It's just a sphere. So it's a sphere. P is kind of a dumbbell shape. Like that, and it could go in several different directions. And then after that, they start to get a little bit weird. Not terribly weird, just kind of weird. So when you get to the D's, they're not just dx, dy, and dz anymore. They become xy, x squared minus y squared, and things like that. So you don't have to, you should remember that there's a px, a py, and a pz. But you don't have to remember dxy, dx squared minus y squared, and all that. You just need to remember the P, as far as the coordinates for the P. Now, the D is, instead of being shaped like a figure 8, it's shaped more like a 4-leaf clover for 4 of them. And that goes in all of the different axes. So you've got an XY, an XZ, a YZ. And then you got one that's a little strange, and it's an X squared minus Y squared. And then you have a Z squared. Z squared doesn't look like a 4-leaf clover. Z squared looks like a figure 8 with a donut around it. So this is a D, and the other Ds look like this. So 4 of them look like this, and 1 of them looks like that. And that should be in section 3.7, I believe. Mm-hmm. So it was the last half of what we talked about. Any questions about how to determine the shape? No, okay. And somebody said, is MS value always a half? And the answer is yes. It's either plus a half or minus a half. Oh, yes, F does have a shape. F's shape is more like this. But we'll get into that when we get into the next section. But I want to talk about the radial distribution function and the probability distribution function. So the electron distribution and the electron density are different. Electron density tells you kind of where is it likely to find it. Oh, more like the one with the donut. But F also has several different weird ones as well. All right, so electron density. Well, there was. Let's see. I got another question here. The last 2 were 4 looks like 4-leaf clover. 1 looks like dumbbells with a donut. Yeah. Okay. So there was a guy, and his name was Schrodinger. Let me spell it correctly. I think his first name is Erwin, so Erwin Schrodinger. And he went on a trip, and then when he came back with this really complex equation. Yes, he's the same one with the cat. He is. He's a little bit sick, in my opinion, with that whole cat idea. And I'll tell you about the cat in the box here in just a second, because you got to know that story. It's pretty strange. But he came back from his trip with a super complicated equation called the Schrodinger equation. And it is my least favorite equation in the entire world. I can work with it. I understand it. I just hate it. It is no fun. But we're not going to do the Schrodinger equation in this class. You just need to know that there is an equation. And then the answers to the equation give you some sort of an understanding of where the electrons are. So when we're looking at the electron distribution, we just want to know kind of where are the electrons. And the shape of the graph goes something like this. And does anybody know why it's not more down there? Yeah, mine do too. Why? So this is saying that at this distance, so this is distance. And this is psi squared, which is the answer to the Schrodinger equation. So this gives you the electron density. The electron density means if I'm looking at an atom, where am I likely to find an electron, a particular electron? Correct. It can't be 0. And the 0 density is right here. So you don't even see the line at 0. But you don't get a whole lot of information from that. You get some information. You get a lot more information about where it can't be than where it really is. Yeah, you're not going to find them right at the nucleus. And that's because of that whole circular wave thing, and it has to be a whole number. Otherwise, it's an unstable wave. So the other thing that we have, so we got this one. The other one that we have is called the electron. So this one's the density, electron density. And this one is the electron distribution. And this one kind of starts at 0 and goes up and comes down, depending on which orbital you're talking about. So if we're talking about an s orbital, then you would only have one pump. And these distribution functions are going to give you, they're basically going to tell you where's the most likely place to find the electron. So in the case of the 1s, it's about 53 picometers from the nucleus. So it's not very far at all. And I don't know why, but my computer is on the verge of dying. So if it dies, then I'll log off here and I'll log on to something else. So I won't be gone for long. All right, so we got about 7 more minutes. We've covered pretty much everything in this section. And we'll get into more detail in the next section. But there's one other thing that I wanted to talk about. So if you have an s orbital, well, if you have an atom, just say you have an atom, you have the nucleus, and you have an s orbital. So this is the 1s, the 2s, the 3s, and so forth. So you know you can find an electron here, or here, or here, but not in between, right? So what you're going to have in the graph of the equation is nodes. And we talked about nodes last time, and that was with standing waves. So if you have a standing wave, they look kind of like this. And a node is anywhere that it's going to cross the 0 line, assuming that this dotted line is where 0 is. And these would all be positive, and these would all be negative. And you get the same kind of node in the electron distribution function. And you can tell how many nodes there are based on what your n level is. Let me give you some examples here. So if n equals 1, you're not really going to have a node. It's going to definitely start out at 0, but that's not really a node. That's just a starting point. And it goes up, and it comes down. And then with n equals 2, it's going to go up, come down, and go up and come down again. The reason is because this would be like the first, let's say you had I was going to say a gobstopper, but not everybody's had that kind of candy. So we'll just say an onion. So if we had an onion, the very center of the onion would be the nucleus. And then you have a layer of the onion. And that first layer is n equals 1. So you're really just given one area that it could be. And then when you get to n equals 2, you have a very slight possibility it could be here, but it's most likely going to be here. But it's not going to be here. So you have a node right here. And it's more likely to find it right there, which would be the second shell. And so if n equals 3, how many nodes do you think you would have? 2. Perfect. So nodes equal n minus 1. So if you have n equals 1, it'd be 1 minus 1, and that's 0, so 0 nodes. If n equals 2, that's 2 minus 1, so that's just 1, so that's 1 node. If n equals 4, that'd be 4 minus 1, so that'd be 3 nodes. And it's just how far away from the nucleus are you going to get at that point is all that it's really asking there. And we've got about 4 minutes. Do we have any general questions about this or anything you want to ask? Oh, the cat. Okay, yeah, the cat. Ugh. The crazy cat. And this is a ridiculous idea.